So in this video we're going to look at the final two examples of Born-Haber cycles that you'll find in your pack. Again, we're going to ask you to pause the video and see if you can fill in some of this yourself. So for the first task, pause the video and see if you can use the definitions to write equations, paying particular attention to what the 1 mole is about. So pause the video and have a go at filling in the table. So there's the first one. It asked us to form sodium oxide, so we're forming 1 mole of Na2O from its elements in the standard states, and that's the equation we've got. Form 1 mole of gaseous sodium atoms from the element in their standard states. Atomisation. And again, another atomisation, this time for 1 mole of oxygen atoms from its element in the standard state. First ionisation energy, where you remove 1 mole of electrons from 1 mole of gaseous atoms. First electron affinity, where you add 1 mole of electrons to form 1 mole of gaseous 1- ion. Second electron affinity, where you add a mole of electrons to the already 1- ions to make 1 mole of 2- ions. So just have another think. Can you remember why first electron affinity was negative but second electron affinity was positive? So the first electron affinity is negative because when a neutral atom attracts, the protons in the nucleus of that neutral atom attract the electrons, that's an attraction, so attractions are formed and energy is released. But for the second electron affinity, a negative ion and a negative electron have to combine, so we have to overcome the forces of repulsion, so energy needs to be put in. And did you get that last one the right way around? Did you spot that this time it's enthalpy of dissociation, so that's breaking down, not forming? This is our unknown. So what else can we think about before we start to try to put this on the cycle? Well, we can look at the fact that there are 2 NAs in sodium oxide and think to ourselves, some of these definitions are not going to match up with my cycle because I'm going to need some more sodiums. Anything to do with sodium isn't going to match up because I've got 2 sodiums and those definitions have 1 mole of sodium. And so I'm probably going to be doing some doubling at these points. We'll have a look at that on the cycle in a minute and see how that works. So what we're going to do is we're going to scroll down, we're going to have a look at the cycle, and we're going to put things on the cycle, remembering our little rules, our little ideas for this. So we put our ionic solid at the bottom, and we're going to work our way from the elements. So this is made from 2 sodiums, solid, the element, and a half an O2 gas, that's the element oxygen. So we're going to work our way all the way around this cycle from the elements to the gaseous ions. So first of all, we need to turn the elements into gaseous atoms. We need to atomise. And the first change I'm going to do is to atomise sodium, but leave oxygen alone, half an O2 gas. And then I'm going to atomise the oxygen, leaving the sodium alone, so half an O2 gas becomes an O gas. Then I'm going to do the first ionisation energy of sodium. Now notice, because I've got 2 sodiums, I'm going to release 2 electrons, 1 from each sodium. This needs a gas state symbol, and we've done nothing to the oxygen. Now we're going to start adding electrons onto the oxygen, so I haven't done anything to the 2 Na+. I've used up 1 electron, so I've still got 1 to make an O-. And then at the very top here, I'm leaving the sodiums alone. I'm adding that second electron onto the oxygen to make the oxide ion. And there we've gone from our elements on the left all the way over to our gaseous ions on the right. So what we need to do now is put the values on from the table. So we're looking carefully at our table. And we're saying the first thing we know is that this from the elements, and this is the correct equation, is -414. And then we know that we have got here sodium solid becoming sodium gas, which is plus 109, but the value in the table is for the equation we wrote, which was for 1 sodium, and we've got 2, so we're going to double that number. This is the atomisation of oxygen, and it's the right amount for the equation, so we just put the number in. Now again, we've got twice as many sodiums as the equation is for. Now the equation for the first ionisation energy is for 1 sodium we've got 2, so we're going to double it. So we're doubling these numbers because these numbers are to do with the sodiums, and we've got 2. Yeah, so these 2s, these are all to do with the sodium. Now the next number is to do with the oxygen, so we're not going to need to double it. It's the minus 141, and I also can double check that I'm putting the right thing in there because it's the minus number and the arrow points down. And this one is plus 791. This big up arrow is our unknown. Now this arrow goes a different way to our previous examples. It goes in the same direction around the cycle as minus 414 does. If you follow minus 414 and x go in an anti-clockwise direction. So mathematically, minus 414 plus our unknown are equal to, all the other arrows are following a clock round in the same direction. They're all going up and round. We can follow them over. So if I just temporarily draw a little line on here, we can follow these arrows all the way up and down and up, and we're still doing the same arrow. They're all going the same direction. They're all going in our clockwise direction, whereas this arrow starts from the elements as well and follows the x all the way up to the top in the anti-clockwise direction. So we're going to add up all our numbers. 2 lots of 109, 249, 2 lots of 494. Oops. Apologies. Pressed on the page there. 2 lots of 494. Plus a minus 141 plus a 791. So get your calculator out. I'm going to pause the video, see if you can work out the value of x. And that's what you should have got. X is 2,519 kilojoules per mole. Okay, so in this final example, we're not going to use this cycle to calculate the lattice enthalpy. We're going to calculate something different. But just like the previous examples, why don't you pause the video now and see if you can fill in the table. So we'll just have a look up to there, because the first two are very similar to previous ones, but spot the difference now. Hasn't asked us for the next one as atomization, it's asked us for the bond enthalpy. And the definition of bond enthalpy is the enthalpy change when 1 mole of a given covalent bond is broken. So when I break one bond between an F and an F, I will end up with 2 F atoms. So this equation is not the same as the atomization equation. You could ask yourself, what would be the value for the atomization equation? So what would be the equation for that, and what would the value be? Now the equation for the atomization would be half F2 goes to F, and so the value would be half of 158, which would be 70, what would it be, 78? No, that's not right. So half of 158, whatever that is, 79, quick maths. So there we go, they're the rest of our equations. Just because there's 2 F's in another step doesn't mean you can write an equation for electron affinity with 2 F's in. The definition says when 1 mole of gaseous atoms gain a mole of electrons become 1 mole of gaseous 1 minus ions. It must match the definition. So why don't you have a go at putting all of that data onto the cycle and having a think, are there any that I'm going to need to double? Are there any things that are going to be affected by this formula? There's our unknown x. So are there any things that I might need to double? Try put the data onto the cycle. So we have a look at a cycle without the numbers first. That should be what we're looking like. We've got our ionic solid at the bottom, and then we've got our elements, and we atomize our metal, and then we are actually going to be using bond enthalpy because that was the data we were given, even though it's similar, well, it's the same process as atomization but with different molar quantities. Then we've done first ionization energy and then second. Check your numbers of electrons. Make sure you've got 1 and then 2. And then we've got our electron affinity, and then we've got our lattice dissociation. So we're just going to put the numbers on that we've been given. So we've been told that this one is the big +1, 2630, and we've been told this one is the -1220. The atomisation was +177. Now, have a close look at this equation that we highlighted in the table up there, the bond enthalpy one. This actually matches. We have the right number of fluorines for bond enthalpy, so we can just copy down the number. We don't need to double it because it wasn't atomisation we were given, it was bond enthalpy. Then we've got first ionisation energy at 590, and then second at 1100. Then we've got our unknown, but our unknown is for one fluorine, making one fluoride ion, and we've got two fluorines, so we've got 2x. And that is the only number that we need to double in this cycle, because that is the only number where the number is for 1 mole of actual fluorine, given that our formula has 2Fs in it. The bond enthalpy is for 2 fluorines, so we only actually have to double this electron affinity value. So we're going to have an answer of 2x when we do some algebra, and we're going to have to find x. So let's have a look at how we could algebraically set that out. Again, you start from the elements and you work your way around the cycle. So if you were to go the clockwise route, yes, that way, then you would be adding up all those, and our anti-clockwise route would be the other way. Let's go around this, back up. That would be our other two numbers. So we can algebraically say -1220 plus 2630 equals all the others added together. 177 plus 158 plus 590 plus 1100 plus 2 lots of x. Now x should turn out to be a negative number because the arrow points down, but we're going to do the work. So pause the video, get your calculator out, add it up. And there you go, I've got -307.5, if I want to put units on, kilojoules per mole. So take a bit of time and look through these Born-Haber cycles again. I'm sure you'll find many that you can practice in the study packs and your exam packs.